Alright, in this video we will be covering the very first lesson of Unit 2, which is Analyze Piecewise Defined Function, and this will cover Worksheet 2.1. Worksheet 2.1 is the first worksheet. It only has 4 questions, so I'm only going to do 2 of them. I know there's not very many questions here, but there's only 4 questions total in the worksheet, okay? So I'm going to do questions number 2 and 4. Okay, so I drew roughly question number 2 here. If you look at your worksheet, you'll see that the points that we have here match exactly the same. I have a point at negative x equals 1, negative 1 for y. I have this parabola shape function here. We have this parabola at x equals 3 and y equals 7. So we have this coordinate point 3, 7. And we have this line over here on this left side, okay? So we have 2 functions going on here. Before I go on answering the questions that they ask on this problem, we need to review a few things. We need to review the definition of increasing. So let me write down a few things here if you missed my notes. You have to understand what something that is increasing. Okay, something that is increasing, a part of the graph where it is increasing, we will find a positive, the slope will be positive. Okay, so every increasing portion of the graph will have a positive slope, something going upward. Okay, and then we also need to remember decreasing. If something is decreasing, a portion of the graph is decreasing, then the slope will be negative. We'll have something going down. The graph is going to look like it's going down, some sort of decrease like that. Okay, either linear or curvy, a decrease. Okay, and constant, a portion of the graph that is constant, the slope is 0. The slope, we have a zero slope. So constant graphs are like this shape. It's always, there's no slope, there's no incline or decline, it's just a 0 slope. We also have to pay attention to another vocab, which is open interval. The word open, we want a domain, an interval in the domain. So we want an interval in the x-axis, but we want it open. So whenever they ask me for an open interval, we will use parentheses. Okay, so the open means we're going to be using parentheses. A lot of the students get confused because they see parentheses and they see 2 numbers inside. They think it's an order pair, but this is just an open interval of the domain. If I want an order pair, I'll use the word coordinate. Okay, if I use the word coordinate, then I want an x comma y. Okay. So open interval, we'll use parentheses. A coordinate, we also use parentheses, but you have to pay attention to the vocabulary word. Also, another thing we need to review, it's something that we've been doing it for the last 4 weeks, is domain. Okay, domain are the x values. Domain are the x values, and range are the y values. So we will be asking you for an open interval, and this open interval will be the domain. Okay, we're going to ask somewhere in the domain, a interval in the domain, that the function is increasing, decreasing, or constant. And then we'll also ask you for some specific coordinates, and we'll also ask you for domain and range. The 2 specific coordinates we'll be asking, those are all the important notes right here. The 2 specific coordinates we'll be asking is the relative maximum, the relative max, and we're also going to be asking you for a relative minimum, okay? Maximum and relative minimum, okay? We'll be asking you for these 2 important coordinates. Now, these are coordinates. These are points. These are points in the graph that are the maximum point, a relative maximum point, and this is also a point in the graph, which is a relative minimum. Now, a relative maximum, every time I'm looking for a relative maximum in the graph, there's always a change in the graph, and this change goes from from increasing to decreasing. There's always a change, and from increasing to decreasing, and we find a relative maximum. And a relative min, there's always a change, and it's from decreasing to increasing. Something that was decreasing and then it became increasing. If you look in the neighborhood of the graph, this is a relative min. If you look in the neighborhood of this graph, something that changed from increasing to decreasing, if I just look at this neighborhood right here, I will find a relative maximum. Okay? So it will make more sense when we apply all these words right here that's going to be used into this graph of number 2 right here. Okay? So when I look into this graph of number 2 over here, the first thing that they ask me is state the open interval of, or intervals on which f of x is increasing. So we have this function right here, we're going to call it f of x. And they're asking us to show what interval, and it says open interval. And that's question letter A. In what open interval is this function increasing? Increasing. So I look over here on my graph and I see, well, from -6 to 0, my function has a negative slope, is decreasing. But from 1, right here at x equals 1 to 3, if I frame this entire function, if I narrow and zoom in just from here to here, I see that this function is increasing. So from x equals 1 to x equals 3, if you look in your graph, you see that this little portion of the graph is increasing. Okay, you're going uphill right here. So we have to use an open interval, we have to use parentheses. And we're saying from x equals 1, from 1 comma all the way to 3, this graph is increasing. Okay? They ask for open interval or intervals. Sometimes you have more than one. And I look at this graph, I see decreasing, and then I see an increasing portion, and then I see another decreasing. So there's only one increasing portion. Okay? Now in letter B, it asks for the open interval. Again, open means parenthesis, interval, or more than one, intervals, and where the function is decreasing. Okay? Where is it decreasing? So I look it over here, back, I see from -6, if I frame it right at -6, all the way to a +1, if I frame my function right here, I see that it's decreasing. So from -6 all the way to a +1, from -6 all the way to a +1, that is the interval in where the function is decreasing. And then it switches from 1 to 3, to increasing, and then it picked up again from +3, x equals 3. So from x equals 3 to infinity, because I have a arrow, from x equals 3 on to infinity, positive infinity, this graph is going to be also decreasing. So from +3 to infinity, positive infinity, my graph is going to continue to decrease. Okay? So those is just analyzing the graph. Where is it increasing? Where is it decreasing? And we always are using the x values. This is the main axis here that we focus the interval, okay, that we refer to the interval of increasing and decreasing. Another question that they ask is the domain and range of this function, and that's part C. They ask for the domain. I'm going to use the letter D, and they also ask for the range. They do not tell us which kind of notation to use, so I'm going to stick to interval notation. That's one of my favorite to use. I'm going to stick to interval notation. If you like inequality notation, you're okay to use that as well. My domain looks like my graph stops here. It has a cap on. It has a closed circle right there. So my domain starts at -6 and is included, so I'm going to use a bracket from -6. Then all the axes here, x values, are part of a graph, at least one portion of the graph. And then 3 is also part of my graph, 3, 6. and then 4, and then 5, and then 6, and then it goes on forever in the positive infinity. So, and that goes on forever. Okay, so as you can see over here, it kind of matches what we were talking about for intervals of increasing and decreasing. Okay, now the range, we're looking at the y values. I'm no longer referring to x values. I'm going to be looking at up and down on my graph on the y values. Okay, the y-axis. That's for my range. And I see that this function goes on forever here. Goes on forever. So there is no lower value here on the y. It's going to go on from negative infinity. And if I'm trying to frame my graph, it stops right here at 7 because the highest point is at 3.7, 3,7, and nothing goes higher than here, the 3,7. But all the y values below are values of my range. It will be part of the graph. So from negative infinity to y equals 7. So from negative infinity all the way, y values stops right here at 7. I have a closed dot at 7 and a closed dot here as well. So I'm going to put a bracket. That's my domain and range. And those are my interval where something is decreasing, increasing, decreasing again. My domain is the x values. My range is the y values. And then it also asks on letter D for a relative minimum. So relative minimum. I'm just going to write relative min. So I'm trying to find a value here, a coordinate, and this is a coordinate. Okay, this is not an interval. I'm trying to find for a specific point on this graph where it changes from decreasing to increasing, and it marks the lowest point on my graph. So let me scan the graph from left to right. If I look here, this is a really high point. There is no difference, there's no change from increasing to decreasing. I'm looking for a minimum value anyway. So here's a small value. It changed from decreasing to increasing. So this is a minimum, it's a relative minimum. If you just zoom in on the graph right here, you see that that point 1, negative 1 is the smallest value relative to this area of the graph. So one of the coordinates would be 1, negative 1. It is a relative minimum. Then I scan the graph a little further. I find a high point up there, and this is going to go down forever. I don't have any other relative minimums. This is a minimum relative to the graph. This is a minimum right here. Okay, of course this graph is going to go on forever, but relative to the graph, to this area, this is a relative min. In part E, it asks for a relative maximum. Okay, now I'm looking for a really high point on my graph, a relative maximum. If you look at your graph, that's pretty high over there. Okay, that's a high point, but relative to the graph, to a little interval in the graph, there's not a change from increasing to decreasing. That's just actually a starting point, so that is not considered a relative maximum. And here's a relative min, and we are suspecting that that has something to do with the maximum value. If I switch it from increasing to decreasing, relative to what happened here, from increasing to decreasing, this is a maximum value. So I switch it from increasing to decreasing here. Relative to what happened here in this area, 3,7 is a relative maximum. 3,7 is a relative maximum. And I really don't have any other maximums anywhere because this graph is going to go down forever. It never comes back up. And that's pretty much what I have for my graph. Okay? So that's relative min and relative maximums. And we talked about open interval for increasing, open interval for decreasing, domain and range, relative min and relative max. But this question also asks for us to create a function, a piecewise defined function for this graph. Let me see if there's room here on the bottom. We're going to create, and it actually tells us, it gives it away that it has to be, you have to be able to see two functions going on here. I do see two functions. I see, if I stop here at x equals 1, I see a linear, a line coming down here. And if I frame it from x equals 1 on to positive infinity, I see a parabola. So I am going to create a function, f of x equals, and it's going to be two functions. One is going to be a linear. I like to write it down so it guides my thoughts. One is going to be a linear, one is going to be a quadratic, a parabola, okay? And I'm also going to define, because it's called a piecewise define function, I'm also going to define the domain. Where does this function linear lives? Well, the linear lives from -6, is located between -6 and +1. So between -6, including -6, all the way to +1, we have our linear. And I remember the equation of a line. It's always in my mind. Y equals mx plus b. The reason I'm using that equation is because I do have a y-intercept, and the b is the y-intercept. So in this case, the b value would be 0, and the slope, that's all I need for my y equals mx plus b. The slope, it's dropping 1. I'm running 1, dropping 1. So if I start from any point on the graph, it looks like I run 1, drop 1, run 1, drop 1, run 1, drop 1, and it keeps on going on running 1, drop 1. So it's running 1 and dropping 1. It's a -1. So y equals mx plus b. I have the m, I have the b. I can write my equation. So this is going to be, here's my y equals, is already here. Y equals, the slope is -1 times x plus a 0. I don't need to write that. Okay? And that is the equation of my line. If I keep on graphing this, I would be running 1, dropping 1, and yes, it would work. Okay? Now we need to write the equation for the parabola. Okay? The equation of a parabola has a stretch, the letter a. Now it's y equals a, x minus h squared plus k. The h and k are my vertex values. I already have that. So I can go ahead and plug in a 3 and a 7. So it's going to be x minus, there's my +3 squared, and my k value is a 7 plus a 7. I just need to find my stretch in front of the letter a here, which is my stretch. If you look at your graph, which has a much better grid in the back, you'll be able to see that all you have to do is drop 2 and run 1, and you would already find another point on the graph. Okay, let me show it to you here. Here's the graph that you have on your homework. There's 3,7. Notice that if I drop 2 and run 1, I already found my stretch. So A is going to be drop 2, run 1. Okay? Because the run is a 1, I can use this stretch. Drop 2, run 1, I can use it. If the run was anything less than a 1, this would not be useful. I would have to pick a point on the graph, plug it in to solve it for A. And I showed you how to do that on previous videos. So now I know what the stretch is for my graph. This A is a -2, so I come and put it over here. And it looks like I am going to be graphing this parabola for all of the axes that are greater than 1. So for all axes that are greater or equal to 1. So notice I chose to put an equal for 1 here and not here, but you can choose to put it anywhere you want. So here is the equation for the graph of the above, the equation for the above graph is a piecewise defined function. Here's all the analysis we did it on this graph. Where is increasing? Where is it decreasing? Where do we have a maximum? Where do we have a minimum? So, and this is what we would like to be able to do, is analyzing a piecewise function. Okay? All right? Let's do number 4. Number 4 right here. We're going to be asking exactly the same questions. Take a look at your graph. I'm going to use the graph here. It looks much better here on this paper than on mine. All right, so let me see if I can zoom in a little bit more. Just a little bit. There you go. All right. So let's take a look here what we have. We're just going to go through this a little quicker than before. It looks like I am increasing right here from 0 to a 1, because there's my x value of 1. I'm going to label this a 1. Looks like from 0 to 1, if I frame the graph, I can see it increasing. I'm going up. If I frame from 1 to 2, it looks like we're decreasing. And then from 2 to a 3, we're increasing again. And then from 3 to 5, we're just constant. So now that I have an idea of what's going on my graph, I can answer the questions on the side here. It says, state the open interval, so I know it's open, means parenthesis, on which f is increasing. F is increasing from 0 all the way to 1. We see this increasing portion of the graph, and then it decreased, and then it picked up again from 2 to a 3. So from 2 to 3 is also increasing. Okay, so we took care of that portion. And then state the open interval on which f is decreasing. I see it decreasing from 1 all the way to a 2. It is decreasing, and that is the only portion of the graph where it's decreasing. And then it says, state the open interval on which f is constant. So we see it from x equals 3 all the way to x equals 5, this portion of the graph right here. So from x equals 3 to 5 is constant. And now it's asked me to state the domain and the range. I'm going to put D for domain and R for range. Okay? Now the domain is x values, just like the intervals. So I see that it started at 0, included 0. So I'm going to put a bracket for 0. And I went all the way to a 5. There's no arrow, so I am stopping at 5. Okay, so included bracket because we have a closed dot. So that's the domain. We covered the entire domain of the function. Now for range, we look at the y values. Okay, I'm going to frame my function from the bottom to the top. And it looks like the smallest y value is 0 right here. So include the 0, and it goes all the way up to a 3. Y equals 3, and I have closed dots there. It is part of my function, so it's also a bracket. Now it's asking me, state the coordinates. It is a parenthesis, and that is the actual point of any relative minimum. So I'm looking for the smallest value relative to some change on the graph. This is small value, but there was no change around here. If I frame this function here, I don't see any change going. That's actually the starting point. And then I increased, I decreased, and I went up again. So relative to what's going on right here, we have a minimum value of 2, 0. So a relative min would be 2, 0. And it looks like we don't have any more minimum values because we go up and we stay up there as a constant. And then state the coordinates is an order pair, x, y, but I want a maximum value. So it looks like if I go up, I hit a really, really high value here, 1, 2, and then I come down. So relative to what happened here in this section, 1, 2 is a relative maximum. Then I found a minimum here, the bottom of a hill, and then I went up. I found a really high point, but I never came down. Because there's no change relative to what's going on here, this is not a maximum value. Okay, I went from increasing to constant, and that does not count as a relative maximum. So that is the only maximum we have. Now, write a 3-piece. So somehow I'm supposed to see 3 functions here. I can see the parabola, that's function 1. And then I see a linear, an increasing linear. That's number 2. And then I see a third one right here. So I do see 3 functions. I'm going to write f of x equals, I'm going to write it down the 3 functions I see. First, I see a quadratic. Then I see a linear. I see an increasing linear. And then the last one I see is also a linear, but I'm going to write a constant. And that is the easiest one to write, because a constant is just a y equals a certain number. And it looks like y equals 3 in here. Okay, so that is an easy one to write. Y equals 3. I'm sorry, I lowered the paper here. Okay, y equals 3. Let's go ahead and define where this function y equals 3 lives. If you look at the graph here, from 3 to 5, that's where our constant function is graphed. So from 3, all the x values in between, all the way to a 5. Okay, so that was an easy one. Let's take care of this linear right here. I don't have a y-intercept, so I'm not going to use y equals mx plus b. I'm going to use the other form of equation of a line, and that is y minus y1, or the k value, equals the slope times x minus x1, or x2 and y2. This means all I need is one point on the graph, any point on my line, and the slope. That's all we need. Any point that I can plug in here, it will create my equation and the slope. So I'm going to pick this point right here, 2, 0. 0 for y and 2 for x. So I'm going to plug that in. And I don't have a whole lot of room to work on here, but I can rewrite it right here. Okay, let me see if I can work on it right here. So I have y minus a 0, because that's that 0 point right there. And the slope, we need to count the slope. It looks like we're going up 1, 2, 3, 4. Yeah, that didn't work. Let's keep on counting, see if we can find it. Up 1, 2, 3 over 1. That might work. Let's check it again. Up 1, 2, 3 over 1. 1, 2, 3 over 1. Yep, that works. So it looks like we're going up 3 over 1. And then we have the x minus the 2 value right there. Okay, so there you go. Y minus 0 is y equals 3, x minus 2. All right, so there's our equation. I already have my y equals right here. I can just write the 3x minus 2, 3 times the quantity of x minus 2. And this function only lives between a positive 2, from a 2, all the x values, all the way to a 3. Because I already included the 3 here, I cannot include the 3 here. Okay, only gets 3 in one of the graphs. The last one is our quadratic. All I need is the vertex, which is right there, our relative maximum, and I need the stretch. It looks like we are dropping 1, 2, and we're going over 1. So remember, this is a 1 right there. So it looks like we're dropping 1, 2 over 1. So I am dropping 2, that's my stretch. X minus, there's my 1, that's my h value, squared, plus my k value, which is 2. And this function is only graphed between 0 and 2. So if all the x is between 0, including the 0, all the way to a 2, I'm not putting an equal on the 2 because I already put it here for the 2. Okay? So there you go. And I analyzed this function. Writing equations of lines is something that we did last unit. So this should not be new to you. I'm going with a lot of details here, but this should be something you've seen before. All right, so there you go. I hope this video helps you with these 2 questions, and I will create another one for the next section. Thank you.